Great, thanks a lot. Welcome, everyone. So today I'll talking about Delta Lake, but more importantly, I'll be talking about the recent innovations we have done in Databricks and how we integrate with Delta Lake. So let me just set the context. I think you have seen this slide, but let me just quickly go through this. So this is the destination is the Lakehouse, and just to set this up, you have your unstructured and structured data in the data lake, and then this is where Delta Lake gives you the asset transactionality on top of that data lake, and then you have Photon for performance and Unity Catalog for governance on top of that data, right? So these are the key pieces of the Lakehouse. So today, Michael announced that now Delta 2.0, a lot of innovation coming in, a lot of the new features we have released in open source. And this is one of the graphs that he showed, that if you look at Delta Lake using open source Spark, Delta is 4.3x faster than the other storage format. But then what happens when you take the same Delta Lake and you put it on the Databricks platform? So this is where the power of Photon and Unity Catalog comes in, and this is where we start seeing some amazing results. Not only that open source Delta was 4.3x faster, but then when you add Photon and UC on top of it, we are now talking about a magnitude faster performance. So in this case, for example, the same benchmark, the TPCTS benchmark, we're seeing 19x performance improvements. So my session, the rest of the time will be dedicated to how we actually got here. What are the things that we have done in the system to get to this point? So let me set the context. How do we think about this problem? How do you actually build the best lakehouse from ground up? And then when we started thinking about this, we took two goals. The first was, how do we provide the best out-of-the-box price performance? And here, the one key thing is, out-of-the-box is one thing. When you start the system, it should just work automatically. But as your workload evolves, how do we actually keep evolving the performance automatically without you bothering understanding the details of the system? And the second thing we focused on is, how do we actually improve query performance for the low latency use cases that are very, very applicable in the dashboarding use cases, BI use cases that we are seeing more and more from all of you. And this is where, it's like combining the power of Photon plus Delta plus Unity Catalog is where we really see a lot of improvements. And two specific things. When we're looking at Photon, we are really optimizing Photon to read and write to Delta in a much faster way. And using UC to actually handle the metadata. And I'll talk about some of the challenges we had that really UC is helping us, Unity Catalog is helping us to solve those challenges for the low latency query performance. So I've divided my talk into two parts. Most of you care about the read query performance and the write query performance. So that's how my talk is structured. And when I talk about reads, I'll talk about how we are getting better file sizes. And I'll explain the importance of all of these as we go along. How do we get efficient data skipping? How do we process the metadata much faster? And then, of course, all of these things not only helps reads, but they also help write queries, specifically data skipping, faster metadata processing, and then just focusing on writes itself, I'll also talk about what we are doing to just accelerate merge performance. So let's talk about reads, better file sizes. So why do you want better file sizes, right? There is a balance here. If you have too many small files, then you are just reading a lot of data, a lot of files, and that can actually impact query performance. If you have very large files, then also that's not very good, because then you are actually not getting good data skipping. You're not able to find the right file to read, and that means there's a lot of inefficiency in the system. So how do we get better file sizes out of the box? We have this awesome thing called optimized writes, and especially for unpartitioned tables, because partitioning, when you partition a table, you actually are dividing the clustering the table. But it's much harder to actually get good file sizes when the table is not partitioned. And then with optimized writes, now we are writing out good file sizes. automatically out of the box. And throughout my presentation, I'm presenting some of the results that we saw for that particular scenario. So in this case, for example, we see a 2x performance improvement with optimized writes out of the box by just coalescing the data. So instead of shuffling the data, which is actually in some cases, it leads to slowdown in performance, we're actually just coalescing the data and writing out good file sizes out of the box. Again, second item we did in having better file sizes is asynchronous auto-compaction. So up until now, the problem with compacting files is you have to sacrifice your write query performance. So when you are writing and you're now suddenly compacting those files, the other queries that are waiting to write, they will suffer from performance. So what we did with asynchronous auto-compaction was we broke this interdependency between compacting files and writing. We made it completely asynchronous. So what that means is that auto-compaction now runs automatically in the background, and it does not conflict with business transactions. And it's actually smart enough to realize that, OK, if a business transaction is coming, it can actually roll back to let the business transaction go through. So that we also see a great result with auto-compaction. This is just mainly coming from the fact that you have better file sizes, and we see something like a 1.6x performance improvement with auto-compaction. So that was about better file sizes. Now, the whole reason of having good file sizes is that you then can get good data skipping. So when a query comes in and you have, let's say, a date filter, or you're trying to find a specific customer, if you have if there is better data skipping, if the files are clustered in a way that we can actually go and find the right file, you get really good performance. So how do we actually get good performance out of the box? That was the challenge. And one thing we realized that in most of the analytics data, a lot of the times, the data is actually automatically sorted by time, right? If your sales data is coming, finance data is coming, in a lot of the cases, the way the data is coming is how it is queried. So if it was yesterday's finance data that was generated, had a yesterday's timestamp, it's automatically sorted in that order. And if we are able to persist that sort order, we are able to write data in which it came, we automatically get clustering, good clustering out of the box. And now this is being rolled out with Photon. Now when you write out the data, we automatically maintain the natural clustering order, and we see some amazing results. Here, what you see here is on the x-axis, we have 3 different scenarios. In the case of ingest, you notice that there is no performance impact, so the team worked really hard to make sure that there was no degradation in performance while maintaining the insertion order. But at the same time, there is performance improvements on, for example, here we chose a delete query, and in the other case, we had a simple select query. And you see something like a 19x performance improvement completely out of the box just because the data is sorted. And when the query goes in with a date filter, it's able to go and get the right files. So that was the case of when the data is automatically sorted. But then you also have cases where you have to particularly sort the data based on your business needs. So for example, based on a certain region or your customer ID. And Z-order is a super popular way of doing this, of co-locating data. But up until now, running Z-order, it takes some time. It can be quite laborious process to run the Z-order. And so we started looking into, OK, how do we improve the performance of Z-order? And this is where we saw some fantastic results with Photon, where we actually made running Z-order, writing files, not only faster, but the key thing was that as we noticed that as you add more columns to Z-order, previously the performance used to go down, which is obvious because now you are sorting more data, it's more complicated, you are writing the zone maps in a more complicated way. But with Photon, we see the consistent query performance for Z-order. It's a 5x performance improvement, which is pretty awesome. So then, so this was all about out-of-the-box performance, but then what do you actually need to do for low-latency dashboard experiences? And this is where we started looking at how our customers were using Databricks, and where was the time being spent in the query processing. And we actually noticed that in a lot of the cases, it was metadata processing where most of the time was being spent, especially for the dashboarding queries. As much as 40% data overall was being spent just in processing the metadata itself. The second key insight we saw was that a lot of the data was actually not really big data. It was actually small tables. Today, on Databricks, on Delta Lake, we have tables, and Hagai will talk about it for Akamai, for example, which are hundreds of petabytes. But it's really the small tables where this issue of latency comes in, and most of our customers are actually creating small tables on daily basis and then processing those tables. So then we focused our direction towards making metadata processing really fast and improving the query performance for small tables. So one of the first things we did was, for really small tables, the time it took to read the metadata from the objects, such as S3 or ADLS, it would be as much as actually reading the data itself. So then we started thinking, OK, how can we make that faster? How can we actually improve the query performance by reading the metadata for the small table much faster? So we introduced this thing called checkpoint prefetching. We're actually reading the checkpoint in a much faster way, in a much more scalable way, without waiting for Spark to actually process the metadata, because there isn't that big of a delta log, so you can actually read it much more easily directly by parallelizing the I/O from the driver itself. And we saw a 3x performance improvement for small tables when we are reading the metadata. Then we focused on, OK, how do we improve? So that was for the small tables, but how do we actually improve query performance for large tables? And this is where actually working with Akamai really helped us, where when the tables are hundreds of petabytes, the log itself can be in gigabytes. And this is where we started thinking, OK, how do you actually scale the processing of the metadata itself? And this is where we introduced the column pruning for the metadata itself, where we were putting the metadata, clustering the metadata itself based on the query, and then querying it in a much more efficient way. And the result we saw was something amazing: 5x performance improvement for large tables for metadata processing. And the last thing, so the Parquet file itself has some metadata. It has headers and footers. And then when you're actually querying the data itself, there are multiple API requests being made to query those files. This is like classic software engineering work, where we actually went through the code and started looking at each API call that was being made and understanding whether we can actually optimize it and reduce it. And the result was we actually eliminated more than 75% of the API calls. So before, Delta would make like 7 API calls. The query engine would make 7 API calls to Delta to read it. And now with Photon, we reduced that by 75%. So this not only made the query processing for small and large tables faster, but also reduced the storage cost, because a lot of the cloud providers actually charge by the number of API calls being made. So this was all about read query performance. Read query performance is important, and as I mentioned, some of these efforts actually help write query as well. But then what about purely writes? Writes are important too. They are actually a big use case that customers, that Delta Lake supports on the Lakehouse. And then one thing we noticed was that a lot of our customers were actually doing merges on Delta Lake. Merge is the single most popular operation on Delta Lake. So our goal was, OK, how do we make merge faster? How do we actually give customers a great merge performance out of the box? And this is where we introduced low shuffle merge, where instead of up until low shuffle merge, what would used to happen is that the data, so generally merge has changed data and unchanged data. And the unchanged data would get shuffled and then get rewritten once the merge is committed. But we started looking, OK, do we actually need to shuffle the unchanged data? Do we actually need to keep rewriting these files when we are committing merge? And these are some of the improvements we made. We actually reduced the shuffling of the existing data and made the query performance awesome. And these are some fantastic results. So here what you see is we have 3 scenarios. In the first scenario, there is no Photon. There is no low shuffle merge. In the second scenario, we just switched on Photon, and you see a 4x performance improvement. And then the last scenario, we switched on Photon and low shuffle merge, and then that's where you see a 8x performance improvement. It's completely out of the box, switched on automatically by default. So let me just summarize. So out of the box, our goal has been how do we give out of the box performance that actually adopts as the workload evolves. So in terms of reads, we have the better file sizes, optimized writes, asynchronous auto-compaction, efficient data skipping, preserving the natural sort order to get good data skipping out of the box, making Z orders with Photon much faster, and then the fast metadata processing, processing the small tables, making them really, really fast, and then the large table metadata processing as well, just making it really scalable. And the last thing is Parquet metadata fetching, just reducing the number of API calls to make it super fast. And then lastly, accelerated merges for low shuffle merge. So let me just give a quick sneak peek into the future, and then I'll pass the mic to Hagai. So our goal has been low latency and out-of-the-box performance. So let me talk about some of the few things we are doing in the low latency stuff. One of the things we have been now focusing on is, as I mentioned, processing metadata. It takes a significant portion of the query time. And so how do you actually make metadata processing even substantially faster than all the changes? And this is where we are now running into the limitation where if you put the metadata into the cloud storage, such as S3, you are limited by the latency. You are limited by the fact how fast you can access that object storage. So this is where our goal has been to build a metadata caching service for faster query performance. This will especially help with small table query performance, and it will avoid the latencies that are introduced by various object storages. So some customers have a different experience on S3, and sometimes they have a different experience on ADLS and Google Cloud Storage. So now you get a consistent experience across 3 clouds. The second is express commits. So up until now, the time it takes to commit a transaction has been a function of the number of files, which generally can be a function of the size of the table. So as the tables grow bigger, as the number of files grow larger, the time it takes to commit becomes larger as well. So we have been breaking that dependency, and the way we are doing it is by avoiding the full state reconstruction with every new commit, and to give the consistent performance. The third thing, which Michael also talked about in his keynote, is deletion vectors. So up until now, every time you would do a merge, what would happen is we would rewrite the existing data along with the new data, right? This is the write amplification problem. And with deletion vectors, our goal is to just write the new data without rewriting the old data, and then just have a pointer to say that, OK, this is the new data. This is what we need to read. So we're seeing some really good performance improvements in our internal testing, and we're very excited for the community and the customers to try this out. And then lastly, we have noticed that a lot of the customers talk about, hey, I have to run optimize, I have to run a vacuum myself. So we have been focusing on, OK, how do we make these processes completely automated for you and do this out of the box? So one of the goals has been that running this operations automatically based on certain budgets that you will set. So that's one of the other items that we have started working on as well. And these are the results that we see from our own internal proof of concepts. These are very early results, but we are seeing some dramatic improvements. So for example, with metadata caching service and express commits, we are seeing anywhere from 5x to 50x metadata performance improvement. This 5x to 50x slider depends on the size of the table. So for really large tables, we are seeing some dramatic improvements. And then, of course, if the table is small, then the time it takes to commit wasn't that slow anyway. So the improvement is small. Overall, the query performance improvements that translates from this 5x to 50x, it's about 4x query performance improvement. And these are preliminary results, but they're still very, very exciting. And then our last goal is that no manual intervention is needed for you to get good performance out of the box, so not running optimized Z-order or stuff like vacuum. So with that, let me invite Hagai on the stage to talk about awesome experience Akamai has been having on the Lakehouse.
Thank you, Himanshu. This is great stuff, by the way. We can't wait to try this on our workload, especially around the metadata stuff. Hi, everyone. I'm Chagai Atias. I'm a senior software architect at Akamai. Just a little bit about Akamai. For those of you who don't know, we are the largest CDN and cloud security provider. Numbers talk about 30% of internet traffic are going through the Akamai's network, and we have around 350,000 edge servers, which are distributed globally to route all this traffic. And what we do, actually, we collect security events that were detected on the Akamai network, and we use this data to protect our customers. We build security solutions on top of them and provide analytics. And generally, we make the internet fast, reliable, and secure. Let me tell you about the business problem that we have. Our goal is for this type of workload to provide near real-time ad hoc analytics over a very extensive data set. So let me give you some numbers. We get about 1.5 gigabytes a second of malicious activity, about 6 million records per second, which over the course of 30 days translates to 4 petabytes of data just for this use case. And we serve some of the largest enterprises. So think of companies like TikTok, Amazon, Airbnb, Adidas, Nike, and really the latest, the greatest enterprises out there. They are all Akamai customers. They come to us, and we need to provide them with real-time analytics, which is definitely a challenge. So let's talk about some of the challenges that we have. We have very strict KPIs on data availability and query performance. We need to show data within just 5 minutes of occurring at the Akamai network, which leaves very little time for ingestion. So we really need to have a very rapid ingestion. The second thing is that our events cannot be pre-aggregated. So in our architecture that you'll see in a second, we do not have a gold layer. We only clean up the data in somewhat, like a bronze table. Then we have some kind of a silver table, but that's it. When you have over 60 different filter combinations, you can't really pre-aggregate any data. And of course, pre-aggregations adds latency, so we cannot allow that. And then on the serving layer, on the query side, queries can scan hundreds of terabytes of data for a customer and still needs to return very, very fast for the 99 percentile within 10 seconds. So that's the SLA we have there. And we'll not only provide high-level analytics, we also support a drill down to see the actual raw data up down to the event level. Let's talk about this simplified view of the architecture that we have. So we have the Akamai network sending all those traffic. We are running on Azure. We have the receiving layer there. Then we use Kafka to stream all those events. We use Azure Databricks to process the data, and then eventually we store it on Delta Lake. And like I said earlier, you won't see any aggregations here. You won't see any gold layer. We don't fully adopt the medallion architecture just to do this. So let's talk about why we started this journey. Our on-prem system, which was where we were running before, is pretty much falling apart. This is an example of our day-to-day, how our day-to-day used to look like. So we got many customer escalations on a daily basis, and customers were experiencing downtimes and getting errors or getting slowdowns. And eventually, we ran out of any room to grow. We couldn't support any increasing load. If a customer had a big campaign and things like that, we couldn't support it anymore on our on-prem environment. And then we couldn't add any more features or just add more products. Okay, so we chose Databricks because we really wanted to build one Delta Lake that contains everything just once, and we can use it for various different use cases. So for example, we use the same data set to provide interactive analytics, but also we power some reporting and BI and machine learning on top of the exact same data set. So it was the Lakehouse white paper that was the main driver to go go and use Databricks to do this. And we really wanted to go with a managed solution because we wanted to focus on the business side. We wanted to build products. We want to do better with our customers. We didn't want to build a platform that does all this. And we wanted to go with a company that we can partner with in order to help us build this. Now, this was not an easy ride. We did have a lot of challenges, especially around what Himanshu mentioned, metadata handling and all of that. It did take a while to get to where we wanted to get. So let me tell you a little bit about the journey. So we started a POC with just 10% load, and everything looks smoothly. But then we increased the load, and we iteratively, we're identifying bottlenecks, communicating them on a daily basis. We were fixing them together with the team. So just some examples around metadata. We were able to reduce the delta log scan to just sub-seconds in most cases. And then async table state computation for those of you who are seeing those data skipping jobs that are happening. So we were able to make them asynchronously, so not affect any running workload on the cluster. And then incremental commits, which is what Himanshu talked about. I think it was mentioned as express commits or something like that, but that's fine. And then on the caching layer, so working with the team, we went up from, I think, 60% cache hit rate to the very high 90s by just better uniforming the data across the cluster, supporting more than one cache replicas using the cache select syntax. And like I said, improved cache affinity and hit rate in order to meet the SLA we have, especially around query performance. So again, a little bit more on the collaboration with Databricks. We wanted to be more than a client, so we found a company that looks at us as not just another client, but better build a partnership. So we have daily sync meetings with the team and a private Slack channel where we communicate on a daily basis. We have direct involvement from engineering, so we get custom images that are tailored to our scale and solve our problems. And then usually what happens is that those features or fixes are going back to DBR, so everyone earns from it, which is great. And I want to say that we were also able to kind of affect the roadmap because some of the ideas, some of the features really came from the problems that we have on our scale. And then got back into Databricks and affected the roadmap. So this is kind of a summary of what we do, how we power interactive analytics at scale. So we need a really rapid ingestion in order to support this type of workload. And then we do a proactive caching. So what we do, we bring data onto the cluster before it's even needed. So the queries, in most cases, are going to take it from the cache, from the local cache, from the local disk, instead of going all the way back to the storage. And I think Himanshu also mentioned that this is something that in future versions is going to happen automatically. So hopefully you won't need to do that anymore. But this is really helping in order to support or meet the SLA for sub 10 seconds for very large customers. And then on the query side, so like I said, a query can scan hundreds of terabytes of data, shuffle and aggregate them within less than 10 seconds, which is what we need. And this is, again, the 99th percentile. So in order to achieve that, we needed an efficient data layout, a correct partitioning scheme, and a very efficient metadata. We needed to get to a high cache hit ratio, again, high 90s. Efficient query engine, we do use Photon. We get about 50% improvement by just using Photon. And then we definitely needed to have enough resources and bandwidth. in order to support this scale. So just a quick summary of the improvements we were working with the team over the last, I think, more than a year. So we got tens of fixes to eliminate some inefficiencies that we had on the Delta log, which eventually led to build the incremental commits feature, and I think a future feature is also going to be incremental checkpoints, which is coming later this year. Incremental commits, I think, is going to be added in DBR 11.1. So on the Delta cache, so we got improved cache affinity, again, going from 60 to 65 cache hits to the high 90s, which is great. And also support to cache have multiple cache replicas using this syntax. On the vacuum, so we got 47x speed up. Again, we have a lot of data, a lot of tables, a lot of partitions and a lot of files inside them. So vacuuming was a little bit slow, and together with the team and the fixes that we got 47x improvement, which also got into DBR 10.4.1. And the last but not least, since we do have a lot of data that needs to be read from the storage, we had to eliminate or have a better way to deal with object store throttling when you read more than what the storage can give you in terms of bandwidth. So there's definitely some great work that was done by the team around that. And I think that's it. Thank you.
Fantastic deep dive, thank you. Any questions for the guys there? Gentleman in the red shirt.
So using all this extra caching and all, how much percentage does the cost go up?
Say again?
Using all the, using all the caching and all of that,
yep.
How much does the cost go up? Because
how much does the cost go up?
a lot of memory to be able to do all that, right?
Yeah, so actually for doing the caches, the only downside I would mention is not around cost, but it's more around resources, because caching takes resources from the cluster, meaning that your cores are busy with reading the data and then caching them locally. And also, in order to have a cache, you do need a VM that supports caching, so you need a locally attached SSD or an NVMe. Those VM types can be more expensive on most cloud providers, but the actual action of just doing something like this, if you already have the cluster, except for maybe just reading stuff that you're not going to use if you prefetch and no one reads the data, we didn't see any increase in cost just by leveraging prefetching.
So it's better up that usage of what you have.
Yeah.
Yeah. Actually, I would even say that it could even reduce the cost. I'm not saying we've seen it, but imagine.
Access, probably. Right? Cloud access cost.
Yeah, exactly. Cloud access or object store access, which saves by just going to the local disk instead of going all the way to the storage.
Right. Okay.
Any more?
I have a question for you. So when you were writing to improve the write performance, you mentioned you did a shuffle merge or a low shuffle merge. Can you elaborate on that? I'm not familiar with the shuffle merge and what do you mean by the low shuffle merge,
Yeah, sure. I have 2 minutes and 30 seconds, so I'll try to do justice. But by the way, there is like a detailed documentation, and I'm happy to point you to detailed stuff. But the main idea is, so when you do a merge, right, you have the data that is changing, so the new data, right? And then you have the data that is not changed, right? So up until now, what used to happen is the data that is not changed, right, it used to get shuffled when we are writing it out as new files, right? So you used to take the old data, combine it with the new data, and write it out as new files. So now what we did is just an internal algorithm change where we actually, instead of, because it's the data remains the same, the old data, right? So the data that is unchanged data, we keep it as is until the last job, and then just like merge it with the last job and write it out. So basically, it's an internal improvement that just like improves the speed with which we write out the files. Yeah.
Thank you.
Thank you, Himanshu and Haggai. Excellent.
Awesome. Thank you, everyone.
Thank you.
Thanks.